Okay, I want to start talking about something called directional derivatives today. Okay, um, let's suppose that z is a function of x and y is differentiable everywhere under discussion here. Okay, so that's differentiable. Okay, and suppose u hat here is a direction vector. Now the hat means that what? This is a unit vector. Okay. All right, now suppose I have some point AB in the xy plane where this function f of xy exists, and so assume that it's differentiable in some wide neighborhood around that point. So all the points under discussion fall within that neighborhood. Okay, we could do the following. We could consider a line or a motion in the direction of u, okay, the following way. So this would give us this line here. Suppose I have what? The points x, y on a line here. I'm starting at AB and I'm moving s units in the u direction. You can see here then, now s is going to be actual arc length, right? Because this is a unit vector. I'm parametrizing with s. Okay, in order to do that, I have to deal with what? A direction vector, a unit vector. Okay, can you see that this is simply saying that what? I'm moving, let's say it went like this. I'm just moving, if s is positive, I'm moving in the direction of s, or in the direction of u from the point AB, okay, s units. Okay, if s is negative, you can see I'd be moving in the opposite direction. But I'm just basically moving along that line there. Now, here's what I'm going to consider. Okay, so s is arc length along that line. Okay, now I'm going to consider then x as a function of what? S, and y as a function of s, because the point AB is fixed, right? That's some fixed point, and u is some assumed particular direction I'm moving. Okay, so u is also fixed. Okay, the only thing that's varying right now then is how far I go out. So if I have s in the positive direction here, okay, I'm moving out here. And then I'm going to evaluate the function at points here on this line. See, at different points. Okay, those points are parameterized by s, right? Z is actually a function of s then, because I'm doing what? I'm taking those values of x and y and dumping them into f and evaluating, right? So z is a function of x and y. So I get this. So you see the ultimate independent variable here is what? S, okay? And now I've written explicitly what that is. Well, x was just a plus s times u sub 1. Y was b plus s times u sub 2. Okay? Now, if I'm going to differentiate z with respect to s, I'm going to use the chain rule here, right? Okay? So I would do what? The partial derivative of x evaluated at the x and y values times x prime plus f sub y evaluated at x and y times y prime with respect to s, by the way. Okay? Now, if I'm talking about the derivative here at this particular point AB, then what I want to do is evaluate this at s equals 0, right? Okay? So I'm going to just imagine evaluating this at 0. So I'm actually going to find the derivative of z with respect to s at the point AB. Now, if I evaluate x at 0 and y at 0 here, the functions, right, I'm actually where? I'm at, if s is 0, x is at a, and if s is 0, y is at b, so I'm going like this. F sub x of what? AB. What's the derivative of x, the x function, with respect to s? And you can see if I differentiate this, I'm thinking of x as a function of s now. If I differentiate with respect to s, I just get u1. Now, a similar argument holds for what? The case of the y's here, and I get ab here, and I get u sub 2. So the instantaneous rate of change of z with respect to s would be f sub x at AB, u1, plus f sub y at AB times u2, and that can be written compactly this way. Notice that that is the gradient of little f evaluated at AB dotted with what? The vector u hat. Okay? This is sometimes called a directional derivative, and it's sometimes written this way. Okay? Because it does depend on the direction you're talking about moving, right? It depends. Well, it depends upon the point you're talking about, but it also depends upon this guy, right? U hat. Which direction are you moving? Directional derivative, cap d subscript u hat of f, and that's typically evaluated at some point, but you could consider it as a function of x and y. But that's going to be the gradient of f dotted with u. Now, what does it mean here? Let's come back here. You see I'm taking the instantaneous rate of z with respect to s at the point AB, okay, when I'm moving in this particular direction. Well, here's the idea. Z equals f of xy. This is some sort of smooth surface, okay? It's some smooth surface. And you imagine there's what then? There's a tangent plane, right? There's a tangent plane at that point, AB, and what the ever corresponding value of z would be, f at AB, right? Okay, so there's a tangent plane to the surface when x is a and y is b, okay? Now, if you imagine that, usually the plane's not, it has some tilt to it, all right? Now, how quickly the instantaneous rate of change of z as you move along this, the line, the instantaneous rate of change of z is the instantaneous rate of change of z along that tangent plane, okay? And that's going to differ from direction to direction, right? Okay? I hope that makes sense to you, okay? Just like, imagine if we have a hill going uphill. Certain directions it's very steep, other directions it's not very steep at all. Okay? But this is directional derivative. Okay? Now, I want you to notice something real quick here. If I go d of, I'm taking the directional derivative in the direction of I, so I write that as I hat here. So I've replaced u hat with I hat. This would be what? The gradient of f dotted with I, right? Just definition. That would be f sub x, f sub y dotted with 1, 0, if I'm using the angled brackets notation here. What is that dot product? Remember, the dot product is a scalar. Some people are still making that mistake. What do I get? F sub y, or f sub x, right? What if I do the same thing where I'm going in the j direction? I get what? F sub y. So I get f sub x and f sub y. Those are the instantaneous rates of change of the function in what? In the x and y direction. Or what? Changes in the direction of the tangent plane at those points, if you want to think of it that way. Okay? So hopefully that doesn't seem surprising here. Okay? But now we're taking it in what? Directions that are different than just I and j. We may be going off in a completely different direction. Let's take an example. Okay? Here's a direction, 1 over the square root of 2, 1 over the square root of 2. You can think about which direction that would be. That's like what? A unit direction in the 45, as a 45-degree angle coming off the positive x-axis, right? That's what that would correspond to. Let's go ahead and just suppose that I didn't even tell you what the gradient was, or what the function was, what the gradient is at, this is supposed to be a little more capitalized, it looks subscript. The gradient of f at some point AB is what? 2, negative 3, let's suppose. Okay? Find the directional derivative in this direction u of the function f at AB. That's probably better written that way because you're evaluating that. This is a function, right? The directional derivative is a function too, but you're evaluating it at AB. Okay? Here, u is the cosine of pi over 6, sine pi over 6. Okay? Okay? So I'm taking it in a direction that's different than what I have written above. That would be what? Corresponding to pi over 4, or 45 degrees. Okay? All right, what would you do here? Well, it's very simple. You just go ahead and compute this direction here. the cosine of pi over 6 sine pi over 6 is square root of 3 over 2 comma a half. And then the directional derivative, or instantaneous rate of change at AB, would just be the dot product of these two things, which ends up being that 2 square root of 3 minus 3 over 2. Okay, so that's pretty easy. Let's do some more here where I actually give you a function. Find the directional derivative in the u direction of this function f evaluated at 1, 2. I should really be using parentheses around these, but if you don't get mixed up, I guess it's okay. Suppose f of xy is x squared y, and my direction, ooh, wait, you notice that I just have a flat on top of this, right? Okay, it's just u bar. What do you notice about this? Negative 3, 4. I want to go in that direction. That is not written as a direction vector, though. Okay, so we have to take that into account here. But this is going to be very easy. What do? You just come over here. You compute the gradient of f. Okay, easy. That would be what? 2xy comma x squared. Yes, okay. And then the next thing you'd probably do is evaluate it that at 1, 2. Okay, just stick in the numbers 1, 2, when we get what? 4 comma 4. Okay, that's cool. Okay, here, because u is not a u hat, right, I have to actually compute the magnitude of this vector negative 3, 4. Turns out to be a nice Pythagorean triplet, so that's actually 5. So the direction u hat is negative 3/5 comma 4/5. And now, if I want to know the instantaneous rate of the change of the function in the direction of negative 3, 4, that is the direction negative 3/5 comma 4/5, I just go ahead and dot that gradient I found, 4, 4, with that direction vector, negative 3/5, 4/5, put it all together, and I think what you end up getting is 4/5, okay? All right? So that would mean what? If you're actually moving this way, if I move 1 unit from this, so point 1, 2, yeah, 1, 2 there, if I move 1 unit in the u hat direction, okay, I would move how many units? 4/5 of a unit in the z direction along the tangent plane, okay, to this surface up here. Z equals x squared y, okay? That's how far I would move. Alrighty? All right? Well, this is really not very hard to compute. It's actually pretty easy here, and I hope you understood. The geometry involved. Your book might have some better graphics involved in this, but pretty easy to compute and to understand, I think. Okay, so I hope you got it.